So backing up again to variables, we spent a little time talking about the quantitative versus qualitative variable, and we're going to come back to both of those after this example and then next week. So other ways we classify variables in statistics are explanatory and response variables. Now that spring is just about here in Eastern Oregon, I hear more birds outside, and as it gets a little warmer, I'm starting to hear crickets. And one thing you might notice is that crickets chirp at different rates. That's a variable. So crickets chirp per minute. Now it turns out their chirps are highly dependent on the outside temperature. That's another variable. And if we were to record crickets chirping and the outside temperature, we'd find that there was this nice relationship to it. And the question here is, which is the explanatory variable and which is the response? Do the crickets somehow control the temperature, or does the temperature somehow control the crickets? Now, there's not crickets everywhere, so I'm going to assume that it's probably the temperature that's controlling the crickets. So I would say outside temperature would be an explanatory variable. It explains why the crickets chirp. So what I'm claiming here is that between these two variables, there is an association. Sometimes that association is referred to as correlation. Now, just because somebody points out an association or correlation doesn't mean there's a reason behind it. So that's another idea. So association and correlation versus cause or causation. So I can look at the temperature outside and I can monitor the cricket chirps. And I can see that as the temperature goes up, the crickets tend to chirp more. So I have all these data points, and the data points seem to be lining up. And it turns out if you look up studies on this, you can see they make a pretty tight line. There's always variation in nature, so sometimes things aren't so tight, they can be more scattered. So the kind of graph I'm making right here is called a scatter plot. And I happen to draw a line through it. Line is kind of optional. But I believe there's actually a cause behind this, that the temperature is causing the crickets to chirp more. Could I graph this the other way? Let's pick a different color. Oops, different color, please. And put the chirps here and the temp here. Graphically, I would still see there's this linear trend to the data, but when I graph it this way, I'm claiming that the chirps are controlling the temperature. But I could have another motive in mind. I usually don't have a thermometer on me, but I can count, and I have a phone or a watch, so I could tell you how many chirps per minute are happening when I hear crickets chirp. So I could listen to the chirps and then estimate the temperature, right? So although sometimes things might be graphed backwards like this, there can be a method to it. So I could count chirps to estimate the temperature, but mathematically speaking, that's not really the way things work. Usually for the causation idea, we put the explanatory variable on the horizontal axis. That's like the independent variable from your old math classes. And then the chirps would be the response to that other variable. Sometimes that's called the dependent variable. So I just want to go over a couple of examples of explanatory response, the idea of association versus causation. Just because there is a strong association doesn't mean there's a causation. And then sometimes in between the two variables, we could have some confounding variable that's really pushing both of them. So in between the explanatory and response, sometimes there could be a confounding variable. That we didn't account for. All right, so next example. So I collected some data. Let me blow this up a little bit. Oops, wrong screen. There we go. All right, so per capita chicken consumption versus Montana precipitation. I chose to put the per capita chicken consumption in pounds here on the horizontal axis and the Montana average daily precipitation over here on the vertical axis. And these points, they're a little scattered, but they do kind of line up. And I can ask Google for some information about this line. So let's do that next, just for fun. It turns out we can measure the association known as correlation between two variables. So they're giving me the equation of the line, and then they're giving me a thing called R squared, which is a correlation, a coefficient of variation. If I take the square root of that, I get R, which is a correlation coefficient. We'll talk more about that in 2 weeks. So SQRT of 0.6 is 0.77. A correlation coefficient is going to be between -1 and 1. The closer to 1 or -1 means these points line up pretty good. The closer to 0 means they don't really line up very well. So 0.77 means, yeah, they kind of line up. Okay, so these points kind of line up here. Now, I have established in my graph an association between per capita chicken consumption and Montana average daily precipitation. Do you think that the amount of chicken people eat in a year affects the precipitation in Montana? We got to know. Gerby needs a brain break. Yeah, that's a good idea. So we'll do this, then we'll take a couple-minute break. So I don't think so. Could we eat enough chicken to change the climate? Oh, wait, we do lots of things that change the climate. Maybe, but probably not. Right? So just because we do have association doesn't mean we have causation. They could be totally unrelated, or they could be several confounding variables in between that are pushing the two of them. Okay, so something else might be going on that's causing people to eat more chicken and causing more rain in Montana. Okay? So there could be confounding variables involved here. So I just have some silly examples of correlation. This one I thought was cute. Number of people who drowned by falling into a pool versus films by Nicolas Cage in a given year. Okay. So when Nicolas Cage made a bunch of movies in a given year, more people drowned in pools. When he made less movies, fewer people drowned in a pool. And if we were to graph these numbers without the years, we would find they make a pretty straight line if we separated the data without the years. Okay, so there is correlation here. Is there causation? I don't think Nicolas Cage, I mean, some of his movies are really bad, but I like some of them too. I don't think people are drowning in pools because of his movies. So it turns out there are tons of things that vary. And if we put them together, we can see that they kind of match up. However, a cause between them doesn't exist, can't be found, or there's many confounding things in between. So we do have to be careful about correlation, causation. This idea was introduced in section 1.3. We're going to spend more time on it at the end of chapter 2 in about a week and a half. All right, so we're going to pause here. We're going to take a little break. And then we'll do just a little bit more work playing with quantitative variables. So get up.